Thank you very much for being here. It's my great pleasure to introduce my colleague and friend, Antonio Acín. So I'm just going to give you a brief summary of who he is and where he is coming from. So Antonio Acín studied the bachelor's in physics at the University of Barcelona. He's also an engineer in telecommunications from the Polytechnic University of Catalonia. After that, he did a PhD in theoretical physics at the University of Barcelona, following a postdoc at the University of Geneva. After that, he moved to the Institute of Photonic Sciences in Barcelona, and he had been there ever since. He's a very well-known researcher in the area of quantum information theory, etc., etc. So in particular, he's interested in quantum information theory, especially in the characterization of entanglement and quantum non-locality, and in quantum communication protocols, with emphasis on quantum cryptography and randomness. So it's a great pleasure that we could convince him here to come this week, particularly in the celebration of the 80th anniversary of the foundation of the Institute of Physics. So thank you for coming, it's a great pleasure. And he's going to talk about, if I recall the title correctly, is quantum information theory with black boxes. So thank you very much.
Okay, thank you for the introduction, and of course thank you for the invitation. It's a pleasure to be here. It was not so hard to convince me because it was nice to come here, and I was curious about the UNAM. It's a well-known place, and it's my first time here, and I'm enjoying my stay. I don't know about the slides, whether I can... So, well, the purpose of my talk is like presenting you, I would say, the main research direction in my group in the last 10 years. And so it's a colloquium type talk, but so it's quite general, but you should feel free to. Okay, es mi culpa, sí, perdón. Muy bien. Okay, sorry, it was my fault. I didn't realize. Okay, good. Coming? Is it? Yes. Okay, so yes, I'm going to tell you about this. I mean, this is a sort of informal talk as a motivation, and it's like a sort of new approach that we developed in my group, among others in Europe or in the world, which is an idea about how to construct quantum information protocols that present some advantages. But some also another of the objectives of my talk is that tell you that this new approach to quantum physics might be beneficial for other applications of quantum physics in other scenarios. Okay, so my position, I'm an ICREA professor. ICREA is a Catalan institution that pays salaries for researchers to work in Catalan institutions. I mean, you don't need to be Catalan to be an ICREA professor. In my case, I'm Catalan, and I'm hired by them. They pay my salary for me to work at ICFO. And these are the funding sources that support the research I'm going to tell you about. So this is it's a rather general public talk. So I will start by saying things that might be obvious to you. So I will start by introducing the field, my field, quantum information theory. And basically the field tries to answer a very simple question, which is what happens when you encode information on quantum particles. So somehow, this is something that this question was posed at the end of 19th century and 20th century for physics. So experimentalists were able to make this transition, so they were going from the macroscopic scale to the microscopic scale, and they had to invent a new theory for that. This is why they found quantum physics. So now we are somehow exploring the same transition, but for information devices. So we know how physical devices behave at this scale now, after quantum physics. Now we want to do the same for information devices. And well, this is very clear why this is happening now. This is just happening because our information devices become smaller and smaller, okay? So it makes sense, and we are now at the position of putting information on atomic particles, and we know that atomic particles are described by quantum physics. And the interesting thing is that somehow physics matters, and I think this is a very deep message. Okay, it's not my message, but I want to give you this message, and I want you to think about it. Because, so some of the question is whether by changing the laws that govern the devices where you put information, whether you can do things that are new. And if you had asked me this question when I was finishing my university degrees, as Isaac said, I'm a telecommunication engineer and a physicist. So if you had asked me, like, okay, come here, tell me, do you think that if I encode information on quantum particle, this is going to imply a change on the things I can do with the information? I would have said no. Okay? Because one of the nice things about information theory is that it has nothing to do with physics. Okay? So information theory is usually seen as a mathematical field, or for mathematicians and engineers. But actually, it's right the opposite. Okay? So the fact that you change the physical laws of the devices in which you put information allows you to do new things. Okay? So I don't know if for you this is a deep message. For me, it was. Okay? So my understanding of information changed because of quantum information theory. Physics matters when you deal with information. And why it matters is because when we use quantum effects, we can design more powerful computers, have secure cryptography, and some other applications. Okay? And in my talk, I'm not going to talk about quantum computation. I'm going to focus on cryptography. Okay? And people then, what they did, they invented protocols using quantum effects to exchange private information in a secure, sometimes people say unbreakable way. I will come back to that, using quantum effects. Okay? So I will now present you the basic idea. This is like a short course on quantum cryptography during my talk. I assume that everyone here knows about quantum physics. It's so simple that I guess you will all understand that. Okay? So I'm going to tell you about the first and most the famous protocol of quantum cryptography that is called Bennett and Brassard, BB84 for Bennett and Brassard, who invented it in 1984. Okay, so what's the idea? The idea is just a protocol in which two parties, the usual honest players in cryptography are called Alice and Bob. They want to establish a secret key. And later they will use this secret key to exchange information. So what is a secret key? A secret key is a list of bits on Alice's side that are shared with Bob, and they are unpredictable by the enemy. Okay, so the goal of this protocol is that Alice and Bob end with a list of bits that are identical. Okay, this is the aim of the goal. So what Alice does is she generates bits on her location, and she encodes the bits on a quantum particle, say a spin 1/2 particle or a photon, a polarized photon. And she sends this photon to Bob. Okay, so if she wants to send a 0, she prepares, I'm going to use a spin language. Okay, usually they send it with photons, but I'm going to use the spin language. So if she wants to send a 0, Alice prepares the photon in the z direction or in the x direction. So she can choose between sending the 0 in the z, spin z plus z or spin plus x. But I assume that everyone knows these things, in the audience? Okay, good. And whenever she wants to send a 1, she sends either the spin pointing down or right. Okay? So this is the encoding. So she chooses to send a 0 either z or x, and a 1 with minus z or minus x. So she sends this to Bob, and now Bob measures the incoming particle in the z or x basis. Okay? He performs a Stenger-like measurement. So, and he chooses this basis randomly. Okay? So there are two possibilities. It may happen that Bob chooses the same basis as Alice. Okay? Here, I am assuming that Alice chose, she sent a 0 in the z basis, so she sent this, and Bob measures in the same basis. Of course, if you send a particle pointing z and you measure z, you're going to see +1. Right? So Bob said, oh, I got a 0. But if Bob chooses the wrong basis, if you send a particle pointing z and you measure in the result x, you're going to get plus or minus with probability 1/2. Okay, this is standard quantum physics calculation. Okay, so in the previous case, Bob was able to read information because the bases were aligned for the preparation and the measurement. In this case, this is bad because Bob gets result plus and minus 1 with probability 1/2. It's the same as if Bob had removed the particle and generated a random bit on his own. Okay, so there is no information. This is bad. So what they do, they remove all those cases. Okay, so they only keep, so they say, Bob says, I measure in the x direction, and then Alice says, keep it, or remove it, okay, depending on whether the bases were equal or not. So at the end of the protocol, half of the symbols are discarded, but for those symbols that are kept, whenever Alice sends a 0, Bob has a 0. Whenever Alice sends a 1, Bob has a 1. And this is going to be the secret key, you see? List of bits that are perfectly correlated. Okay, until now, it seems a very stupid way of sending zeros through a channel. Okay, because you can tell me, well, I can do this in a much easier way by just sending zeros and ones. Okay, of course, at the end of the protocol, they will have 0 and 1. Okay, well, this is because there is something missing here, which is I have to prove you that this is secret. This is a key, but I have to prove that this is secret. Well, I'm not going to prove it, but I'm going to tell you why you can prove that it's secret. And for that, I have to introduce the third player in any cryptographic protocol, which is the enemy, okay, the eavesdropper. So usually this enemy is called Eve. I didn't choose this name nor the gender, so it's Eve, okay? So Eve, she wants to read the secret key because she knows that the secret key is going to be used in the protocol. So what she does, she takes the particles. I'm going to present you the idea why this is secret and why Eve cannot read this information, okay? It's much more complex than what I'm going to say, but I give you the intuition. So what Eve can try to do, she can try to read the message while the particle goes from Alice to Bob, okay? But what's the problem with Eve? Eve doesn't know which basis Alice used. This is going to be announced later, but this will be too late for her because the particle will be on Bob's hand, okay? Later, Bob will say which basis he used. But Eve has to interact with the particles while they travel from Alice to Bob. So she has to read information that is encoded either in the Z or X basis. These are non-commuting, non-orthogonal observables. And Heisenberg uncertainty relation tells you that you cannot read information that is encoded either in the Z or X basis. Okay? So because of Heisenberg uncertainty relation, which is something, a basic principle of quantum physics, Eve cannot read the information and the key is secret. Okay? So far, I think it's more or less clear, okay? It's just Heisenberg uncertainty relation in action. Okay, so I think I'm going to skip that. I mean, well, perhaps let me just say that while standard cryptography that we use nowadays is just based on computational security, quantum cryptography is based on physical security. So the protocol is secure because we believe that the particles behave according to quantum physics and that Heisenberg uncertainty relation is true. Okay, so the protocol can be proven to be secure, the information transmission can be proven to be unbreakable because we assume that the particles are described by quantum physics. Okay, then there are people, smart people, who proved that the protocol is secure. Very nice. So now quantum cryptography is perhaps one of the most mature quantum information applications. If you want to secure your messages with quantum cryptography, you can do it. There are companies who sell you quantum cryptography. Nice. Then some years ago, there was a group of researchers who went to the most famous company doing that. They bought these devices that I'm telling you they are secure, and they hacked them. Okay? So there were several teams. The most famous researcher on that is, the most active was Vadim Makarov. Here's Vadim, the quantum hacker. And so this is what they did. Okay? So they went to the company, they bought the devices, and they hacked. And of course they made some noise because it was a surprise for the field. And now let's try to understand why this happened, okay? So it seems that I was cheating, I was lying to you because I was telling you that things are secure, okay? And now these people went and they hacked the quantum cryptography devices. So we learned from this attack, okay? So Makarov, these hackers, they collaborate with scientists and we learn from their attack. So what did we learn? So the first thing you have to understand is that the hackers didn't break the principle, but they broke the implementation, okay? So I was telling you that there is a protocol that does cryptography that is secure because it is based on quantum physics, and people have derived a mathematical proof. So there are several possibilities why the hacking attack worked. One possibility is that they found a mistake in the mathematical security proof, okay? But this is not what they did. There is a second possibility, which is they proved that quantum physics is wrong, okay? This would have been amazing. They would have won the Nobel Prize. This is not what they did, okay? They did something different. When you go to the security proof, even when I presented to you the protocol, I was telling you that you take particles, spin one half particles, you prepare a spin pointing up, down, left, right, and you send particles and you make Stenger-like measurements. So this is the theory, and this is where you prove the security, okay? And for that, you need to prepare states in spin 1/2. So these are states in a Hilbert space of dimension 2. And you have to measure some observables that usually are described by Pauli matrices, okay? And with this mathematical description, you prove security. Now, let's see what the company does, or any experimentalist. Do they use particles living in a Hilbert space of dimension 2? No, they use a laser. Would you argue that the laser lives in a Hilbert space of dimension 2? I wouldn't, okay? Even if in my theories, I know that the laser doesn't live in a Hilbert space of dimension 2. It's a much more complex object. Then, do the provider of cryptography, do they implement an ideal Stern-Gerlach measurement? No, okay? They have an avalanche photodiode detector, for instance, okay? This is where the implementation lives, and this is where you prove security. And there is always a mismatch between the theoretical requirements that you need for security and the implementation. So you have a very nice security proof that applies here, but this is where reality is. Okay, so your security proof, you may even argue that it's useless because it does not apply to your implementation. And actually what the hackers did, they broke the implementation without disproving anything for the security, because the security proof was obtained in some theoretical conditions that are not met in the experiment. So this is just to tell you that if you require a lot from your experiment, that things live in a Hilbert space of dimension 2 and things like this, unless you don't meet these conditions, the security proof is useless. And this connects with a second problem that is common to cryptography, which is a problem of trust. So this is not a problem of quantum cryptography, this is a problem of classical cryptography in general. And I will illustrate this with something that, a very famous case that became public after the Snowden affair. So in many of these documents that were released after the Snowden affair, there was one in which it was shown that there was a cryptographic protocol that had been promoted by NSA, the National Security Agency. So the National Security Agency was telling people, please use this cryptographic solution, okay? Why? Because they could hack it, okay? So it's like, please use that because I know I'm going to read your messages. Of course, I would say that, do we trust the National Security Agency? Maybe not so much, okay? But the problem is that this cryptographic protocol that was promoted by the National Security Agency was approved by NIST, the National Institute of Standards and Technologies. Do we trust NIST? Maybe yes, okay? So they certify things for us. So NIST was saying, yeah, what NSA is proposing is good, please use it. But then it was, after Snowden, we knew that it was not good even if NIST had certified that. So they say, please stop using that. And this is because when you buy a cryptographic solution, you put trust on your provider. Okay, so do we need trust? So in the previous case, you need that the provider has met all these conditions, otherwise the protocol is not secure. And finally, I always use this joke to explain that. I think this joke is perfect for the talk, so even if you didn't understand anything until now, just focus on this joke. So this is Dilbert, that perhaps you know this cartoon. So, and now he wants to check about the random number generator this company is using, okay, and this is the random number generator. And of course, he wonders whether this is a proper random number generator, okay? And as the guy says, the problem is that you can never be sure about randomness, because the probability that a random number generator gives this sequence is the same as any other sequence, okay? So would you say that this is a random number generator? Well, who knows? Okay. So again, you can come to a company and tell you, here's my random number generator. How do you know that this is random? How do you know that this is a quantum random number generator? Okay. So I will show you how in quantum physics you can be sure that something is random. You can be sure that something is cryptographically secure. You can certify things in quantum physics. And for that, you have to change your way of thinking, and you have to think about a quantum information theory with black boxes, hence the title of my talk. Okay? So that was a long story to motivate why we care about a quantum information theory with black boxes. So you have to make protocols in which you don't assume anything about your devices. You don't know whether these are spin 1 particles, photons in phase space, spin 1, spin 3 halves. I don't know. I don't want to make any assumption. Because if I make assumptions, I will require that the provider meets these assumptions. I don't make any assumption, I don't need to trust the provider. So I have to make a quantum information theory for black boxes. Now, if I can make a protocol based only on the statistics that the boxes generate, then I have certified protocols. So this is what you have to understand from my talk. Okay, so I want to make a theory, I want to make protocols where I deal with boxes, because at the end of the day, what you get from a provider is a box. You go to the provider and you say, please give me a protocol for cryptography. Here it is, the protocol. Here are the devices. It's a black box. You say, give me a random number generator. Here's the quantum random number generator. It's a box. So if I don't want to trust what the provider did inside the box, I should make a protocol and deal with the box as if it was a black box. Of course, this might seem challenging. I have to put some structure to play with these boxes. And this is what I put. So I assume that this is a black box. I will assume that this is a quantum black box. And I'm allowed to feed these boxes with classical information, and then the box produces classical information. So if you want to see a way of representing that, you get the box from your provider, and the provider has put some buttons. Okay, this is not the most practical way, but it's a way of representing what I'm going to say. Okay? Or the provider has put a knob that you can put in different positions. So there is button 1, 2, 3, 4, 5, 6, okay? And you can press some of these buttons. Do I attribute any meaning to this button? No. It's just a button. I'm going to call button 1, button 2, button 3. What happens inside the box when I press the button? I don't know. Do I need to trust the provider for that? No, because I see the button and I press it. As a result of me pressing a button, the box produces a result. A way of seeing this result is like, let's imagine that at the bottom of the box there are some lights, and when I press one of the buttons, one of the lights is on. I have 3, 4, 2 lights. I call the light 1, I call it 1, the light 2, I call it 2, and the light 3, I call it 3. Do I attribute any meaning to these lights? No, it's just a light that is on. Do I need to trust the provider for that? No, either I see it or I don't see it. So how do I characterize these boxes? I characterize these boxes by the probabilities of seeing some results, some lights being on, when I press some of the buttons. This is, I'm going to call the correlations between the boxes. I will make things a bit more clear in what follows, okay? So if I can make a protocol that only uses the information about these probabilities, I'm okay. Because if I see these probabilities, the boxes are secure, random, whatever. If the boxes don't agree with the correlations I need, I give the boxes back to the provider. Is there any question? Okay. Okay, I can jump there. So, what I'm going to tell you is that you can do protocols in this regime, okay? And now I'm going to tell you why I can do that. So let's be a bit now more precise. I'm going to formalize a bit what I mean, okay? So again, I will have Alice and Bob. They want to run a cryptographic protocol. They got these boxes from the provider. They can do some actions on these boxes and get some results. And I'm going to write these probabilities. What are these probabilities? Okay, so Alice and Bob spend some time testing and characterizing these black boxes. So Alice presses button 1, Bob presses button 1, and they observe which output is produced. These outputs may vary with probability. Okay, so they may see that sometimes they get output 1 and 1 when they press button 1 and 1. Sometimes they get output 1 and 2 when they press button 1 and 1. They see all different probabilities for all possible results when they press some given buttons here. These are positive numbers that sum up to 1. They can do this for any combination of inputs. So what's the object I'm going to deal with? You see, I'm going to do a quantum information theory, but I'm never going to use any Hilbert space. I'm always going to deal with these objects here. You will see how. So what is this object? It's just a matrix or a vector of numbers. These are positive numbers. These are between 0 and 1, and all these, the sum of these numbers have to be 1 because that's the probability of getting all the results when I make some inputs. So if you want to make it more concrete, this is like you going to a lab, preparing different quantum systems, making different measurements on these systems and getting the results. Which, I mean, you can think of a polarizer and you put the beam splitter in a given position. Position 1, you call it 1. Position 2, you call it 2. Okay? and you get a click in a given detector. This is a concrete way of realizing this, but I don't want to make any modeling of my devices. Okay, so these are positive numbers that sum up to 1. This is the sum of these numbers equal to 1, the sum of these numbers equal to 1, and so on. Now, again, I will now make it simpler because I want you to understand. Let's consider the simplest example, okay, in which these two devices, you can make two measurements and you get two outputs. Okay, you can put a knob in two positions, or you can have two buttons, and you get two outputs, and I'm going to call them plus and minus 1. Before I say 1 and 2, 0 and 1, you name it, that is not so important. So Isaac has one of these boxes, I have another box. What we do, we are going to test these boxes. We are going to understand how they behave. So what we do first, I put 0 and he puts 0. And let's assume that the boxes, whenever I see a plus 1, he sees a plus 1. And this happens with probability 1/2. So what I'm saying is that we put a 0, and half of the times I see a plus 1, but whenever I see a plus 1, he sees a plus 1. Okay, this is 1/2. So what I do, I plug this here. This is 1/2. Okay, this is the probability of getting plus 1 when we measure 0, 0. Now what happens is that when we put 0 and 0, half of the cases I see minus 1 and he sees minus 1. Okay, I'm just inventing a possible situation that I can describe with this. So, you see, 1/2. And of course now these numbers have to be 0 because it means that whenever I see plus 1, it never happens that I see minus 1, and whenever I see minus 1, it never happens that I see plus 1. You see, positive numbers that sum up to 1. I hope this is, any experiment is like this, okay? You get probabilities by making some actions on your lab and getting some results, okay? I'm not inventing anything. This is what everyone does in science. You do actions, you get results, and you write probabilities. So let's assume that when 0 and 1, we observe the same. When I use 1 and he uses 0, we see the same. And I'm just inventing for you. Whenever I put a 1 and I see a 1, then whenever I see a plus 1, he sees a minus 1. When I see a minus 1, he sees a plus 1. Okay, it's just the opposite. Is this something that you can see in nature? What do you think? Do you want to guess? Is this weird? Just probabilities, no? Numbers, positive, and they sum up to 1. Okay, this is something.
You always have two zeros? Or were you inventing?
No, this is I just invented that, okay? For me, you can always put any positive numbers here between 0 and 1 that sum up to 1. This is a possibility that you could potentially see in nature. So if I want to make protocols in this scenario, I have to make protocols that are constructed only from that, because do I need to trust the provider to construct this? No. We just spend some time pressing buttons and seeing the results. Now, you may wonder whether I am a physicist, because I'm not doing any physics until now. I'm just writing numbers, okay? Okay, here's one also of my main messages. The nice thing is that physical principles impose limits on these correlations, on these tables. You can invent numbers here. Not all possible numbers are compatible with physics. Okay, so this is why I can do interesting things as a physicist in this language. So let's see how this happens. Okay, I will impose the first thing, which is something that I guess we will all agree with. I assume that with these boxes, I'm assuming that the boxes don't communicate while I press the buttons, okay? They are separated. Worst case, I do things space-like separated. So I can invoke Einstein's special relativity. So what I assume is that I cannot use these boxes to transmit information faster than light. I guess we all agree with that here, or so basically almost, okay? I'm going to assume that I assume that a special relativity applies to my scenario. So this means that by doing stuff here, I cannot modify what Isaac sees. Because if it was the case, by pressing a button here, if I could modify what he sees by pressing a button here, I could send information instantaneously. Okay, we buy this for the moment. Well, no, for the moment, no. We buy this, okay, for all my talk. So this means that what Isaac sees, the marginal probability, does not depend on what I do here, x2. This is why I write the probability here, the marginal, does not depend on x2. If you give random numbers here, this condition is not necessarily satisfied, okay? So you only have to demand that what a subset of the parties sees, k parties, does not depend on the inputs chosen by the other parties. Okay, so this is just a very simple mathematical constraint. Okay, you will see now, but it gives you some mathematical structure to the set of tables. So again, let me go back to this example. This is the table I was writing. What's the probability of observing here +1 when you input 0? Well, you know, this is the probability of observing +1 and this guy +1 and +1 and this guy -1. This is the sum of these two numbers is equal to 1/2. But if the other party measures 1, is the sum of these two numbers, which is equal to the previous one, so it's 1/2. So you can see that all these constraints are satisfied by this arrangement, which is not necessarily the case if you put numbers at random here. Okay, so this is an example of non-signaling correlations. How much time do I have?
Half an hour.
Okay, good.
But in practice, usually you wouldn't be sure about how they are causally connected, right?
Well, I mean, you can arrange things so that the measurements are space-like separated in principle.
Sure.
Then, I mean, I'm always going to assume that there is no causal connection between these two processes. And I know that I can enforce that by making the measurements so fast that there is no time for light to propagate from one place to another. This is an assumption in my formalism that I can enforce by arranging the measurements so that they are synchronized and they are causally separated, space-like separated. So I'm always going to work on this, okay, in this regime. Now, before the advent of quantum physics, what would have been the way of thinking about how things can be correlated? Well, the only thing you can think is that, well, someone has created these boxes and has written how these boxes are going to behave. Okay, just a way of seeing this that I like is like someone has put a demon inside this box, the demon is sitting there, and this demon has some instructions telling what to produce given the input. Okay, so the instructions are this lambda, the demon is sitting inside the box, the demon sees the button you press, looks at the instructions, and the instructions say, okay, when the button is 1, produce output 3, and then the light 3 is on. Okay, this is the way we used to think about correlations before quantum physics. This is nothing but the Einstein, Podolsky, Rosen correlations, local hidden variable models. I don't know if these names resonate with you, okay, but this is just the outputs of the measurements of the actions are written inside the box. Okay, you see, it's a deterministic function producing the output given the input and something that was in the box before. Is that the end of the story? Well, at the moment, we believe that quantum physics explains everything, and I'm a quantum physicist, so I'm going to assume that the boxes are quantum. What this means is that you go to a textbook in quantum physics, and it tells you that the correlations you may expect are just measurements for box 1, measurement for box 2, measurement for box n. I'm assuming the boxes are separated, so I put a tensor product, acting on a quantum state. So this is just textbook quantum physics, okay? So some numbers are quantum if I can find a quantum state in a Hilbert space. I don't know whether it's a Hilbert space dimension 2, 3, but there is a Hilbert space in which I find a quantum state and measurements that I combine according to the Born rule, and I get these numbers. These are quantum correlations. Okay, what do we know about these sets? I was telling you there is the classical set where the daemon is waiting to get the inputs and produce the output. There is the quantum set, and there is the set of not signalings, those correlations that I cannot use to send information faster than light. Well, what we know is that these sets, I mean, I'm just representing these sets. This will be the space of correlations. I'm very bad drawing, but I hope you understand that the set of classical correlations is a convex set. It's the one here. Okay? Any point here are some correlations that I can write in this form. What is the set of correlations? It's also a convex set, but it's larger. It's the one here with red. So if you give me a table like this. If it's quantum, it's inside this set. And the set of signaling correlations is a larger set. It's the one I'm representing here. Okay, the set of classical correlation is strictly smaller than the quantum, which in turn is strictly smaller than the set of not signaling correlations. So why do we know that the set of quantum? Okay, now I'm zooming in, okay, this part here, just for you to represent. This is the classical, this is the quantum, and this is not signaling. So I'm just representing these objects in a two-dimensional, it's just an intuitive way of seeing these sets, okay? So this is the part quantum, which is larger, okay? Why do I know that there are quantum correlations that I cannot explain with a classical model? I know that because quantum correlations violate Bell inequalities. Okay, now I will tell you what a Bell inequality is in case you don't know it. So this is why I know that the quantum set is larger than the classical set. Why do I know that the non-signaling set is larger? It's because some people proved it, and now I'm going to show it to you. Okay, so I can give you some tables that don't violate special relativity, but you cannot achieve with quantum physics. And for that, a second course, I gave you a crash course on cryptography, and I will give you a crash course on Bell inequalities. Could be that you know them. Okay, we'll see. So what is a Bell inequality? This is the way that was, the way that people showed that Einstein was wrong, let's say, okay? That the local models, the classical models that Einstein wanted to derive to provide an alternative explanation to quantum physics were not possible. Leaving aside these more philosophical implications, a Bell inequality is also something that you describe in the same language with black boxes. Okay, so Bell inequality is like a situation where there is a source that prepares some particles. These particles go to two different places where you make two measurements. Well, some measurements. Here I'm going to use two measurements of two outputs. I'm going to call plus and minus one. So how do people violate Bell inequalities in the labs? They prepare two photons that are in an entangled state, for those who know. These particles, these photons go to two different locations, and you make two measurements of polarization. But you don't need to say all these things for a Bell inequality. Okay, you can just put in these abstract terms. So here I have an experiment where I make these two measurements of two outputs, and I'm going to write this expression. Okay, this is the output of box 1 when I measure 1, and this is the output of box B2 when I measure 1. It's more or less the same as I'm doing all the time the same things. Okay. And this is the output of box 1 when I measure 1, and this is the output of box 2 when I measure 2, and I'm taking the product of these two outputs. Okay, I'm taking this combination. Why do I take this combination? It will become clear now. Now, how are things in classical physics? Well, I mean, if I describe this experiment in classical physics, I assume that the output of this measurement is known in advance. Okay, so there is a prediction for this output. So they all have predetermined values, plus and minus 1. Okay, so let's work, then what's the prediction of classical physics? So there is a daemon here that is going to say plus and minus 1 depending on the input. Okay, so they all are plus and minus 1. So let's compute the value of this quantity. Let me just give an example, okay, in which everyone says plus 1. Okay, so the particles come here, they have instructions, and the instructions say, no matter which input you use, just say plus 1. Let's compute this number here. Okay, so when I measure 1, the box is going to say plus 1, this number is plus 1, and when I measure 1 here, this number is going to be plus 1. How much is it? Plus 1 times plus 1 is plus 1. Good, this is a plus 1. Well, this will be a plus 1 as well, this will be a plus 1, and this will be a plus 1, because they say plus 1, the two boxes, independently of the input. How much is it? Plus 1 plus plus 1 plus plus 1 minus plus 1 is equal to 2. Okay? This is very simple, right? Well, you can see that for any possible combination of plus and minus 1, this number is equal to 2 or minus 2. So on average, this is never larger than 2. Well, if you are, this is just common sense, okay? I'm just telling you some of trivial statements. Okay, what happens is that, okay, I'm going to spend some time here. So we could play this game now here, okay? So you could send Isaac outside, and I could be here, and you could ask me questions, and my answers would be plus and minus 1, and Isaac would be outside, and you could ask Isaac 1 and 2, and he had to say plus 1 and minus 1. Well, we are never going to get a value larger than 2. Okay? Even if we agree and I say, Isaac, I'm going to say first plus 1, and then I'm going to say minus 1, and then, okay? And he has other instructions, we are never going to get a value larger than 2. Okay? We are not going to do it, but we could play this game. Okay, and we will never going to get a value larger than 2. Well, the surprising thing is that in quantum physics this is not correct. So if you have never seen this and you are not surprised, my talk is a failure. Okay, so you can go beyond 2. And you do that by preparing what is called an entangled state and making measurements on these entangled particles. So this means that if we play this game with Acín and we have access to quantum particles, we can prepare this state of two particles. I put a particle in my pocket, he takes the particle with him outside. You make me a question, I take the particle out of my pocket, I make a measurement, and I give you this measurement as an output, and we're going to get something larger than 2. Okay, so again, if you are not surprised, this is a failure. How quantum physics manages to go beyond these two, I think it's sort of surprising. Okay, so here we have an expression that in classical physics is bounded by 2. This is this boundary between classical physics. In quantum physics, you can see that you can go up to 2 square root of 2. Okay? And this is why we know that quantum correlations are larger than classical correlations. And we know that in these no-signaling correlations, you can go up to 4. So I'm not going to tell you how you prove that, but you can prove that in quantum physics you can never go beyond this. And you can go up to 4. What are the conditions that you can get up to 4? Precisely the table I was writing. Why you can go up to 4? What's the probability that these people see plus 1? It's 1 because either they see plus plus or minus minus. What's the product of plus plus or minus minus? It's plus. So this is a plus. This is a plus. This is a plus. And this here, they only see plus minus or minus plus. It's a minus that with this minus makes you a plus, so you get 4. So what I'm telling you is that if you go to the lab, you make an experiment with 2 particles, you make 2 measurements of 2 outputs, and you see this table, quantum physics is wrong. Okay, so this seems as a very innocent table, but it's not. Okay, so I challenge you to see this table. I'm sure you will not find it in an experiment. Okay, so this is just something that you cannot achieve with quantum physics.
Excuse me. Probably you imply it in what you are saying, but there is a strong assumption always in all what you've been saying, which is in the cases of the boxes that you didn't know anything about it, you at least know that they are a stochastic process that is stationary, such that every time that you repeat the experiment, you know that the probabilities are not going to change with time. So that's an assumption. And in the quantum case, it's because you know that you have always the same state. Because I give you always a different state, it will be a mess and you cannot have anything. So you must know that the source always have exactly the same state. And that's a lot of information there.
Yes, okay. So
it's implicit, but you haven't said it.
It's implicit in the way I presented things. You can also leave this assumption and do things, even with things that vary in time. And I will give you an example. So in quantum physics, you can prove that even if you change things with time, the value of this expression is going to be bounded by 2 square root of 2.
I know, but what you're saying is that people are going to repeat the same experiment many times.
No,
so in order to get to the table, you have to know that there is something beforehand that will be always.
Yes, I agree with you. This is for simplicity. I mean, when I do things more elaborate, I don't need that. In any case, let me just then rephrase what I'm saying. If you make an experiment of this type and you see that this value is 4, then you prove that quantum physics is not correct. Because even if things vary, but they vary within quantum physics, there is no quantum physical realization in which I'm going to go beyond 2 square root of 2.
But I can cheat.
How?
If you don't know that I'm cheating, I mean, I can...
You cannot, look, I can tell you later, you cannot cheat because quantum physics cannot go beyond 2 square root of 2.
Because you're making an assumption that the states that you prepare initially are very well defined. And that's always that...
Well, I'm making, no.
Or anything like that.
I'm making the assumption that I'm doing quantum physics, so my state is a vector in a Hilbert space. If you vary that, then you are not talking about quantum physics. For any vector in any possible Hilbert space and any quantum measurements, even if you vary with time, you are always bounded by this quantity.
I'm talking about the protocol, in which you have to have that your black box is not as black as you said. It has to be. You know.
What I'm saying is that I agree.
Change the box every time they do the experiment, then...
I agree with you in my explanation. For my security proofs, I'm doing this for simplicity, but there are mathematical tools that allow you to also deal with this situation. Okay, of course, I agree with you that in my explanation that was not clear, and for simplicity, I was assuming as you will always have. For the falsification of quantum physics, if you observe a violation of this combination of numbers that goes beyond 2 square root of 2, even if things vary with time, you are falsifying quantum physics. You cannot cheat. Because whatever you do with quantum physics, this number is going to be smaller than 2 square root of 2. So even if you change the realization, any realization is below this value. But we can talk later, okay? So I was starting with a motivation for from an information point of view, and then I'm dealing with this characterization of quantum correlation. I think this is a fundamental problem. And the question is very easy, okay? So now you embed me under the assumptions that I repeat the experiment. You give me any possible numbers, okay? Frequencies, and now I have to tell you whether they are quantum or not. In the squares of 1/2, 0, 0, 1/2, I could prove it. Now I give you these numbers. So you are in the lab, you get these numbers, and you have to tell me whether these numbers have a quantum realization. So are these numbers quantum? Who wants to guess? Well, it's difficult, okay? So I can tell you why it's difficult. So let's imagine you are working on a team. You're an experimentalist. You measure this. So you make an experiment with 2 particles where you make 2 measurements and you got 2 outputs. And you count frequencies, as you do in any lab, and the frequencies look like this. Is this quantum? Well, you have a friend who is a theorist and says, look, I think I was measuring photons, polarization of photons, and I got these numbers. Please give me the state and the measurements that give me these numbers. The theorist spends some time, runs numericals. He doesn't find any realization. Then he goes back to you and said, well, I failed. I cannot explain your experiment. And you say, no, okay, I thought I was measuring polarization, but maybe I'm measuring something more complicated, orbital angular momentum. And instead of dimension 2, it's dimension 3. So the theorist goes back to the computer. He tries with dimension 3. He fails, okay? Does it mean that there is no quantum explanation for your numbers? Well, for that, you have to look for all possible Hilbert spaces, all possible dimensions. This is very hard, right? There are many Hilbert spaces. There are infinite Hilbert spaces. So this is why it's very difficult to exclude that these numbers don't have a quantum realization, because I would need to look for all possible quantum explanations. Well, we found a way of considering this problem, okay, through something that, okay, I'm going to skip that because of the lack of time. So basically what happens, the question I want to tell you is, you give me these numbers, I want to know that these numbers, whether they have a quantum realization, so I want to know whether they are in this set. This set is hard to characterize because I have to explore all possible Hilbert spaces. What we did, we found some sets that contain the quantum set and are easier to characterize. So what we do, if you give me the point, I check whether the point is inside one of these sets, say gamma 1. If the point is not in gamma 1, for sure it's not in quantum. If the point is in gamma 1, it may be in quantum. But then I give you another set that is computationally more demanding, but it gets tighter. If it's not in gamma 2, it's not in quantum. If it's in gamma 2, I give you another set. Every set is more demanding computationally, but we can prove that at the very end it converges to the quantum set. So if you give me these numbers, I can tell you they are not quantum. So the theorist has to stop looking for a quantum explanation because there is no. For you, maybe you can start thinking about writing the paper or checking for a mistake in your experiment. So by this, I'm telling you we have ways of characterizing this quantum boundary now from the outside through this. I'm not telling you the details, I'm telling you that we can do that. Now let's go back to protocols. Remember this Dilbert with the random number generator. So how can you prove that things are quantum in the case? Well, you can do it through a Bell inequality. So a way of constructing a random number generator that is certified to be random is through a Bell inequality. So to have a random number generator, you go to the provider, you ask 2 boxes, and with these 2 boxes you run a Bell test. This number has to be random. Why? So you have the CHSH, and you see whether it's above 2. Why this number has to be random? Because if this number was written in advance, it was plus and minus 1, you can never go above 2. You remember this simple proof of plus 1 times plus 1 and things like this? So if the numbers are written in advance, the Bell inequality is bounded by 2. If you see that the Bell inequality is larger than 2, these numbers cannot be written, they are random. Okay, this is just a simple consequence of Bell inequality violation. How random they are, for that you need the methods I was telling you, and you can obtain this curve. So remember, 2 is the classical value, there is randomness? No, the predictability is 1. And as soon as you enter the region of quantum violation, you can see that you have some randomness. Any possible quantum explanation for your data contains some randomness. I'm going a bit fast, okay? But I'm just telling you that this way of characterizing quantum correlations allows us to obtain these curves. So what you have to do, you have to go to the provider, give some machines the violate Abel inequality, and from this you can certify that there is this amount of randomness. And you can trust what you are doing, okay? So you can be sure about the randomness. You can also use this for cryptography. I'm running out of time. But okay, this is, again, the logic is the same. Alice and Bob will observe a Bell inequality violation. From the Bell inequality violation, they will conclude that the outputs are random, so they cannot be predicted by an adversary. And then they can construct a key out of that. Okay, running out of time. So just to summarize, I was trying to tell you why we need protocols with black boxes. That was the motivation. Then I was telling you that for that you need to deal with these correlations, these vectorial probabilities. Then I was telling you that these vectorial probabilities are not arbitrary if you are a physicist. They are bounded by physical principles. And then I quickly told you that using that you can construct protocols for randomness generation and for cryptography. You don't need to put trust for the provider. You have devices, they violate a Bell inequality. They are good for your purpose. And it's a way of, again, in doing that, I'm assuming that the boxes are quantum, but I never use any Hilbert space. They are behind the scenes, okay? They are always there inside the box, but I never impose anything about Hilbert spaces. This is why it's a quantum information with black boxes. And this has some, this approach can also be used in other situations. So I'm very quickly now ending. So there's interesting things in foundations, of course, because an interesting question is to understand why this region here is impossible, okay? Why I cannot see this vector of number 1 half, 0, 0, 1 half, 1, 0, 0, okay? It seems something innocent. Why I cannot see these numbers in nature? Well, the answer we can give is like, because I don't know how to get these numbers by taking a vector in a Hilbert space and putting some measurements and combine them with the Born rule. But I'm not sure if this is a very satisfactory answer. Okay, we would like to understand from another point of view why the numbers here are not possible in nature. Of course, they violate quantum physics. That may be enough for you. Okay, but maybe you can find other arguments explaining why these points are not possible. Then also something that we are doing, is like, how can you observe this in the limit of many particles? And then we were interested, like, how can we detect Bell violations in many body quantum states? Okay, and we also work on that. And then we gave some tools to detect Bell violations in systems made of many particles, okay? And even it was made an experiment that maybe this is interest for you in the group of Philip Trotline, where they took our Bell inequalities and they observed a violation, sort of violation, in a Bose-Einstein condensate of around 500 particles. Okay? This is because in our case we want to see Bell inequality violation because this is the ingredient with which we can make these protocols. And last thing I want to say is that this is, I hope you were sort of convinced that they are nice, but they are challenging. And the reason why they are challenging is because to make the experiment, you have to see a Bell violation at large distances for cryptography. And this is challenging. So this is also a nice challenge for people who work on quantum optics, even theoretical. So I can tell you where the challenges are. This is challenging. Okay, I'm going to skip that because I'm always very ambitious with my talks, you see. I should, very ambitious. Okay, so this is time to conclude, okay? So I was motivating this device-independent approach, this black box approach. If you want, these are certified protocols. You don't have to trust the provider. You see the statistics, the boxes are good or are bad. And for that, you have to see a Bell inequality violation. This is the condition that you need, okay? Because if you don't see a Bell inequality violation, there is always a classical model for your boxes, and you cannot do things that you cannot do with classical physics. Okay, am I saying that the other protocols are not good? Well, they are good, but they require extra assumptions on your boxes. If you want to make protocols without any assumption, you have to see a Bell inequality violation. Otherwise, you can always find a classical explanation. I quickly told you that there are protocols for random generation based on Bell inequality and key distribution. So okay, this I didn't tell you actually, self-testing. So the reason why we're working in my group is because we want to understand the limitations and possibilities of this scenario. I quickly tell you that the implementation is challenging. We have a proposal using single photons that gives you some advantages. I can tell you more if you are interested. And I think this framework of just working with these probability tables and just inputs and outputs is very clean, okay? Because you don't make assumptions, it's just the numbers you see. And it has applications in other fields. And this is the last thing. So I think this is something that is becoming more timely, this question, the question of quantum certification. So now quantum technologies are advancing and people are doing experiments and theories are making protocols, and even there will be companies selling you quantum devices. And then the problem comes like, how can we certify that these devices are quantum? So how can we certify that the device is random? I told you that you can do it based on a Bell inequality, that the device is cryptographically secure. If someone sells you a box, how do you know that this is a quantum computer? So we need to design tools to certify these objects. And I think this black box approach is a good way of doing that. Okay, with this I conclude. Thank you very much for your attention.
Thank you very much. It was a very interesting talk. There are time for questions. Carlos?
I have a question. Can you do something assuming that one person is in the, like there is signaling just in one direction, or if you break that, you cannot do anything?
Okay, if you want to do it in the scenario I was presenting with no assumptions, you cannot do that anything, because as soon as there is a causal connection between your measurements, causal connection means that you may write a box here and then another box in the future light cone of the first box. You can write this as two boxes, but for me this is just a single box. As soon as things are connected, this is a single system. So the reason why you can, if you think about it, you will agree with me. The only reason why you can write two systems is because the systems don't talk to each other. Because if two systems talk to each other, well, you can say that there are two communicating systems, but this is just a single system. Another possibility is only if you put bounds on the amount of communication. Then yes, but then it's an assumption about things, okay? If you don't restrict anything, even if it's just one way, a box that sends communication to the other, this is just a single box.
What happens if Bob is moving respect to Alice?
Okay, so I didn't deal with these things in my talk, so what I need is that the boxes don't communicate, okay? How to enforce that? I think it depends. I mean, also something that we learn with these hacking attacks is that everything you do is based on some assumptions. In my case, that quantum physics is valid, that the boxes don't communicate. Now, how confident you feel about these assumptions is just very subjective. For me, if you go to a lab and you make an experiment where you prepare two photons and you couple these two photons in two fibers and you send one photon here and the other there, and you make two measurements of polarization on these two photons, I think these processes don't communicate to each other even if they are not space-like separated. I would be happy accepting that. If things move, if still things move, but you can conclude that they are space-like separated, I think it's fine. So I don't see any, you just use, I mean, if you want to enforce this non-communication using Einstein causality, well, you only have to write the cones, and so I don't see anything difficult in that, okay? So you only have to ensure that things don't communicate, these boxes don't communicate while they get the input and they produce the output. How you do that? I mean, whatever you want, it depends on your level of paranoia. Worst case, I would say, do things so that they are space-like separated.
So the game that you presented, I mean, the way that you explained it, at least maybe it's more general, but I want to know, it relied on the fact that you have a finite matrix, at least all the examples that you gave. Mm-hmm. For example, if you could, could you extend it so that you can make measurements, I mean, not only two outcomes, but infinitely many outcomes, for example. I mean, that's a situation that you could handle in this?
Yes, okay. So again, for simplicity, I was presenting with the simplest scenario you can think of, in which you put a bit in your box and you get a bit. I was calling 0 and 1 and plus or minus 1, but it's just two inputs, a binary input, binary output. In principle, the scenario can deal with an arbitrary alphabet of inputs and outputs, finite.
Finite.
Yes. So in principle also, you can reach similar conclusions with an infinite range. Of course, there is something you can do. So if you have an experiment that gives you an output with an infinite range, you can divide the x-axis in 2 halves, and I can call negative, I can take the sign of my output. I can always do that, and I can violate Abel inequality in this regime. But of course, theoretically, it would be nicer not to make this discretization of my output and try to keep all the information my experiment generates. Then it happens, so in principle, things should be possible, but it's a fact that the mathematical formalism that we use does not apply so well. So from a mathematical perspective, doing Bell inequalities in an infinite output situation is going beyond this discretization is a mathematical interesting open problem.
So people don't know how to do Bell inequalities in this setting. Is that?
Well, there are some examples, but we don't have, I mean, in the finite case, now everything is clear. So you come to me, I run leaving aside computational problems, you come to me, I could run a program and give you Bell inequalities, like a machine.
Sure.
If you come and you tell me that you make 2 measurements of infinite range of outputs, I cannot do that. Well, now I have some techniques to do that, but this is something that we didn't even publish. So it's open.
Yeah.
It's a mathematical interesting question.
So you have techniques in the sort of countable infinity, I guess, because then there's a continuous spectrum.
I have the techniques for continuous output, yes.
You have for
Yes, now yes, yes.
Ah, cool.
More questions?
So maybe this is not so many interesting question, but so you show that you can show quantum certification if you violate some Bell inequalities. So my question is whether these quantum hackers that you showed in the beginning show that no Bell inequality is
Well,
they show that there is no Bell inequality violation.
it just follows, yes. I mean, because they hack, the statistics that was generated in the experiment didn't violate any Bell inequality. Actually, the hacking attack, you remember this BB84 protocol I was presenting you at the very beginning? This is the protocol they hacked, okay? By construction, this protocol never violates a Bell inequality because Alice prepares things, puts information, and goes to Bob. So the boxes are always causally connected, similar to what you said before, like information going from one place to another. So this preparation and measurement is always causally connected because there is a particle flying from one place to another and bringing the causal connection. So you can never violate a Bell inequality in this scenario. So in this scenario, unless you make some assumptions about the particle moving from one place to another, you will never be able to prove security in a device-independent way. The reason why there is security is because people assume that the particle that creates the causal connection between the 2 boxes is a qubit. But this is an extra assumption that I don't want to make. In a black box approach, the only way you can prove security is through a Bell inequality, meaning 2 or more boxes, but let's say 2, with no causal connection.
So with this implementation of the quantum cryptography, you cannot secure quantum certification.
Unless you make assumptions. So if you are, let's say, if you are paranoid like me, I want to deal with I don't want to make assumptions about my system is a qubit because I don't trust the provider. He can tell me, I swear I prepare a qubit, even if he's my friend, okay? It comes to, actually, the provider of this company is a very good friend of mine. So even if he comes to me, I can promise you, I prepare a qubit. Well, I don't want to put trust on you, on your preparation. Okay, many things can go wrong if you are an amazing experimentalist. So if you are paranoid, and I don't want to trust the fact that the particle is a qubit, then you have to use my techniques. Now you can say, again, it's a matter of assumption, you'd say, no, I trust this guy. I know he can prepare qubits. Then it's secure. So it's just a matter of assumptions. And it happened that this assumption about qubits and qubit measurements was too strong, as proven by the hacking attacks. So they were wrong. That assumption was dangerous for your security. So it's always a matter of assumption. In my case, I don't want to make assumptions. I want to work with these black boxes. The assumption I make is that the boxes don't communicate. This I agree. And that quantum physics is correct.
Any other questions? What is self-testing?
Okay, so self-testing is another way of certifying. So there are many applications, if you know about quantum information theory, there are many applications in which you want to prepare what is called the maximal entangled state of 2 qubits. Okay, this is the singlet state. Again, you come to me, I'm a provider, and you tell me, Antonio, I need a box that produces a singlet. I will tell you, here you have your box. And you look at it and say, does it prepare the singlet? I will tell you, yes. Well, I mean, how do you know? Okay? So what happens is that the only way you can get a violation of 2 square root of 2 of the CHSH is by a singlet. Among all possible ways of measuring states in quantum physics, the only way of getting 2 square root of 2 is by measuring a singlet. So what you have to take this box, make a Bell experiment, and if you see 2 square root of 2, I mean, this is a theoretical result because you will never see 2 square root of 2, okay? But if you see 2 square root of 2, you know that the box I sold you prepares the singlet. You are self-testing the box I was selling you. It's not only that you are certifying that something is random and secure, you are even certifying the box that is inside the box. This is an even stronger way of certification.
Antonio, you are in a place where many important developments in this area are taking place or are commented. So could you share here for the people, what do you think are the interesting subjects now, because it is all the hype about quantum computation or quantum encryption, but how is the status of that, and how do you think it will go in the next years in this quantum technology, quantum basic research?
Okay, so I'm a basic scientist. Okay, so for instance, let's think about cryptography. If you talk to the companies, well, the challenges they have is to convince the customers and clients to buy quantum cryptography. So it's not a solution that has been adopted by the community. I think this may change, but let's say it's not something that where we can do much. Okay, some people have to convince clients to buy quantum cryptography. So I think an interesting problem to me, and I would like to see more, is how to make all these nice constructions more practical. Because what you need if you want to be paranoid, as I was presenting you, and you want these 2 people to establish a secret key, they have to see a Bell violation at distance. This is very challenging. So something that I spend some time thinking is how to make a way of Alice and Bob distributing entanglement in a way that you can violate a Bell inequality. Another promising approach in this sense, which I also like, is like, okay, what if I'm not as paranoid as I was presenting, and I simplify things in the experimental realization? So there are proposals to make certified random noise generation, in which the only assumption you make is that your box has a bounded energy. I think this is a very reasonable assumption. If you are dealing with light, you can assume a bound on the energy of your light pulse, because otherwise you will burn the experiment, okay? And people are trying to make ways of certifying that something is random just based. So I think there is an interplay between which assumptions you make and how simple things behave in the implementation that is nice. As a general perspective, I think this certification point of view is very interesting. So as I was telling you, there are many experiments in which people prepare quantum simulators. So they have an output, and they cannot simulate this output with a classical computer. Well, this is the advantage of a quantum simulator, that you can do things that you cannot do with a classical computer. But then how do you trust this if you cannot simulate with a classical computer? So I think all this certification, we are facing a very interesting moment in which, with our limited computational capabilities, we have to say something about some very complex quantum scenarios. And I think this certification, you can name it, I mean, the characterization of these complex quantum many-body setups with our poor classical methods, I think it's also very promising. So it's challenging and promising. well, I think this is something that excites me, and I encourage you to work on that. Yes.
Okay, maybe we should postpone the questions because there is some food outside and the rest. So,
Okay.
well, thank you very much.